Good afternoon, everybody, and welcome to the second in a series of 4 webinars on climate science in water systems to inform adaptation and resilience to climate change. And this is hosted by the CIWEM presidential team and the president of the British Hydrological Society. And we will introduce ourselves in a moment. So just some general housekeeping before we make a start. So this webinar is being recorded, subject to getting permissions from the speakers and there being no copyright issues. The webinar will be put up on CIWEM's YouTube channel in the next few weeks. It is worth checking out that YouTube channel because there's lots of really interesting formal webinars as well on all kinds of topics. If you experience any technical issues and you need assistance, then please use the chat function. And Barbara Woods from HQ is on standby to help you with that. If you have any questions, please do ask them, but use the Q&A facility rather than the chat to ask questions. So if you want to direct your question to any specific speaker, then please do so. Although when we are chairing the panel session later, we may put that to other speakers as well to give different perspectives. And an hour's CPD is attributable to this webinar. Okay, so some introductions from myself and Duncan Faulkner then. So if people haven't met me before, my name is Hannah Burgess and I am the current president of the Chartered Institution of Water and Environmental Management. Over to you, Duncan, for a brief intro.
Hello everyone, Duncan Faulkner, President of British Hydrological Society, and I'm very excited about today's topic because I've been interested in the impacts of climate change on flooding and extreme rainfall for quite a long time, really dating back to the floods in Cumbria, where after a succession of floods, I started wondering, can you really keep on telling people, sorry, you've had yet another 100-year return period flood? So really looking forward to today's talks and the discussion that follows.
Yeah, thank you very much, Duncan. So, and Duncan will be joining the panel at the end of the presentations as well. So if you want to find out more about CIWEM and about the British Hydrological Society, we introduced them more on the first webinar, so you can watch the recording of that, and you can also look at both of our websites to find out more. So as I mentioned, this is one of a series of 4 webinars. This is webinar number 2. So today we are focusing on climate science and latest climate science that informs decision making on flooding. And we'll be looking at the latest research on flood extremes, considering rainfall intensity, peak river flows and volumes, and sea level rise. And just as a recap, and for those who missed the first webinar, this ties in very well with the CIWEM presidential theme for this year, which is about adaptation and resilience, and particularly on the scientific element, because we strongly believe that we need the latest scientific evidence to inform decision making on resilience and adaptation. And that's what you will get by joining our webinar today. Okay, so now I'm going to introduce our first speaker. So I'll stop sharing and Felipe will start to share while I introduce him. So a big welcome to Felipe De Mendonca Fileni. Felipe is a PhD candidate in the Water Engineering Department at Newcastle University, supervised by Hayley Fowler. His research focuses on UK hydrology and the development of reliable national scale datasets for community use. Driven by a commitment to translating scientific evidence into actionable insights, Felipe aims to bridge the gap between academic study and the real-world application. Before beginning his PhD, Felipe gained valuable practical experience as a civil engineer in Brazil, where he worked on reviewing urban drainage projects for local authorities, and his academic and professional journey reflects his dedication to addressing practical challenges in flood hydrology. So over to you, Felipe. Thank you.
Thank you, Hannah. I hope everyone can hear me. Well, as Hannah presented me, I'm a final year PhD student from Newcastle University. And what I'm going to be presenting today is how does the UK translate climate change projections into pluvial and fluvial allowances. This is the result of my PhD work and a publication that we've done together with Hayley from Newcastle, Liz from Manchester, Fiona from the EA, and Emma and Mark from SIPA. And those are all my supervisors for the PhD too. So to start off, I figure it might be a good idea to give a brief introduction on what are climate change projections and what are climate change allowances. The climate change projections are basically the result of a physical model that will try to replicate atmospheric conditions and give as output variables such as precipitation, temperature, wind speed for different climate change scenario conditions. So a 2-degree warming, a 4-degree warming, etc. And what climate change allowances will do is they will take these projections and try the anticipated change in peak river flow and peak rainfall intensity according to the projection scenario. This is what I'm going to be talking about. How do we translate that to that? And for that, I think the idea is to give a brief introduction on how it began and how we are right now and where should we improve after. And it all began more or less in the 90s when the first projections for the UK started appearing, and those are the CCRG 91, 96, and the first official projection, which is UK CIP 98, in a model that had a very, very coarse resolution compared to today. The resolution was measured in degrees, and it was more than 200 kilometers square resolution for the grid that was used at the moment. The science that was used to translate this projection to guidelines was also very experimental and very new. Only very few catchments were used, and these catchments were put into a lump model to predict river flow. One curiosity is that even on very coarse resolution and very basic models, the conventional 20% increase in river flows that was used here in the UK for decades was already the result of these studies. In terms of guidelines, it was also very new. The thing that was established in terms of guidelines in the 90s was the precautionary approach, in which you try to prepare for the worst case scenario. There was not too much guidelines in terms of percentage, rather than applying a percentage, applying a freeboard for climate change. That was the guideline in the 90s. With that comes a new cycle in the 2000s with a new set of projections, UK CIP 02, on a new model and a much higher resolution grid, still using daily timescales. In terms of science used to translate these models into river flow allowances, we were still using a small sample of catchments, but instead of using lump models, the first few semi-distributed models, which are a bit more complex, started being used to translate these projections into river flow allowances. Another thing that was very novel was that this science actually started being implemented into the guidelines. The technical report from DEFRA and the EA from 2004 is probably the staple that remained for a long, long time here in the UK. And it established the 20% climate change allowances for river flow in England and in Scotland for a long time. Then it comes a new cycle in the 2010s, and a new cycle always starts with a new set of projections. This time UK CP09 on, again, a higher resolution grid. But the novelty in this cycle were actually the local projections that appeared a bit later, in which we had a very, very high resolution grid and a temporal resolution that was also early as opposed to the daily ones that we had in the past. In terms of science that was used to translate these projections into allowances, we were using a much bigger sample of catchments, and we already had good national scale coverage to get the river flow allowances and more catchments that were modeled with semi-distributed models. But the big novelty in this cycle was the introduction of rainfall allowances or pluvial allowances using the local projections, so the very high resolution projections to establish a percentage increase in the rainfall for climate change. In terms of guidelines, the fluvial allowances were like the national 20% increase was replaced to regional fluvial allowances. So instead of having a percentage increase for the whole territory, we had allowances for every region in the UK. The pluvial allowances were also established in the guideline for 3 different regions in the UK, the East, the West, and the South. Nowadays, what we have is we have the fluvial and the pluvial allowances. Starting off the fluvial allowances, we have the fluvial allowances that are done on the UK CP18 model, the regional projections, which are projections at 12 kilometers square resolution and daily temporal resolution. One novelty in this new cycle that we are into today compared to the UK CP online cycle is that for the fluvial allowances, we are using a fully gridded model covering the whole UK. And these allowances are very complex. They are based on the catchment response to climate change. They have different time horizons. They have different emission scenarios and low, central, and upper estimate. In terms of guidelines, the allowances are still separated by river passing regions. So every region has a percentage increase expected, and that's the one you have to use. The precautionary approach remains until today, where you use the highest percentage increase that you will find in a flood risk assessment study. For the pluvial allowances, we are using the UK CP18 local. So those are projections at a very high resolution and at an hourly temporal resolution, so a very high temporal resolution too. The science is also very complex, so it's gridded at a national scale, using different rainfall durations, using different return periods, different time horizons, and a low, central, and upper estimate as the fluvial ones. One new improvement on the guideline of today is that these allowances, instead of being separated in 3 very big regions, they are also separated by regions as the fluvial allowances, and still precautionary approach is the name of the guidelines in the UK. So we still use the precautionary approach for the pluvial allowances too. So this is where we're at today. Are we in the right track? The reality is that we have new climate change projections that are released regularly, and they increase in spatial and temporal resolution. They also increase in accuracy because we're representing new physical phenomenon, or we are improving the representation of physical phenomena in the projections. There is better science with increased computer power. So at the beginning, we were at using very few catchments to actually get results on very specific locations. And now we have very good result coverages. And we're also using different projection ensembles in which we can derive a lot of climate uncertainty in the results that we have. In terms of guidelines, we have guidelines that compared to the beginning are much more well-structured. We have a very good spatial coverage for these guidelines, and they are also mandatory as of today. So if you're doing a flood risk assessment, you have to use the climate change allowances. So what should we do next to improve our guidelines? The first aspect that I want to touch upon is that we do need more than just a percentage allowance. So the way flood risk assessments are done today is you use a very simple percentage increase in the flow results that you're going to get from your model. And this single percentage is often not enough to represent the very high variability of rainfall events that we have in the UK and the very different moisture conditions that can be on a catchment. Of course, it's very hard to develop a complex model when you're using it to apply to just one specific scenario, but still we need to find a compromise between a procedure that's scientifically accurate, more so than just adding a percentage, while keeping the method simple and applicable on a large scale. Another thing that I wanted to talk about is that the needs of practitioners should be met. So by studying hundreds of flood risk assessments that were done in Scotland, this is more or less how they are done in practice. So the first thing that you're going to do when you're preparing a flood risk assessment is that you are going to apply one of the FEH or REFH methods. Then you are going to apply the climate change allowances to these methods. And then you are going to pick the most conservative estimate, so known as the highest flood peak that you're going to get from these results of the models that we've used. The issue of applying the allowances to these methods is an issue on FEH statistical, which is a method that uses only flows. So there's not really a way of applying rainfall allowances in a method that uses only flows. So usually what's done to actually apply the allowances is you have to sort of finesse the regulation. You have to apply the allowances based on the results of REFH, or you reduce the analysis only to methods that are rainfall runoff models, or you use nested catchments to have different flows to compare and then get a conservative estimate. This is not necessarily ideal, and we need a way of actually representing rainfall allowances in all of the methods. Another point that I wanted to touch upon is, well, precautionarity is all based on you have a large spectrum of results that you are going to plan adaptive measures based on the worst case scenario that you have. But is our spectrum broad enough? I ask that because the fluvial allowances that we are actually using are the results of only one hydrological model, when we have results of several different hydrological models here in the UK. I think the Cypher in Bristol, Shitran here in Newcastle. And these results all point to different scenarios. So if you really want to be precautionary, you have to take into account all these results to prepare for the worst case scenario. Another issue is that there's only two key models available for flood risk assessments. Those are FEH and REFH. And again, we have a variety of models that can be used and should be used to actually be precautionary and have different estimates of flow. The last point that I want to talk about is small catchments and how they need to be better represented in flood risk assessments. So the issue here is on fluvial allowances, and they are scientifically not recommended for catchments that are smaller than 100 kilometers squares. Analyzing flood risk assessments, you can see that they are still used anyway. For instance, in Scotland, analysis that we've done for more than 100 flood risk assessments in Scotland, 88% of them were done in catchments that were smaller than 100 kilometers squares. So we're using inappropriate allowances for 88% of the flood risk assessments that we do. And the reason why we use these allowances and they are inappropriate is because they are done at a daily resolution. When to actually catch the flood response on a small catchment, you need higher temporal resolution to understand the phenomenon that are happening in small catchments. And these allowances then need to be calculated using projections that are at a high resolution, at a Nordic resolution, for instance, as it is done on UKCP 18 local. The issue for that is that we need to calibrate the model also at a sub-daily resolution. So we need flow data at a sub-daily resolution. This data has recently been made available by the EA and SIPA. But we still need this sub-daily data to be reliable, which is what we've been doing in the past 2 years here in Newcastle. And this is the idea. You need data to calibrate the model, and then you need this model to actually calculate the projections using a higher temporal resolution projection. This is kind of what I wanted to talk about. My conclusion is that there's a lot of progress that has been done in the UK, but there's still plenty to do. Thank you. I hope I didn't overrun that much. I'll pass to Hannah now.
Yeah, thank you very much, Felipe. We're now going to move to our next speaker, Donna. Just as a reminder, if you have any questions, please put them in the Q&A. and we'll come back to them in the panel discussion at the end. So by way of introduction, Donna is a senior technical advisor in the National Flood Hydrology team at the Environment Agency. Her team provides evidence and advice to inform flood risk management and incident response. They also update and manage the Environment Agency's flood estimation guidelines to ensure they align with current best practice. Donna is a member of the Scientific and Technical Advisory Group, known as STAG, of the Flood Hydrology Roadmap. Donna has been at the Environment Agency for 4 years, and prior to this, she worked in consultancy, academia, and at the Norwegian Water Resources and Energy Directorate. Sorry, that should say. I'm going to hand over to Donna now. Thank you very much, Donna.
Okay, thanks, Hannah. I'm now going to discuss non-stationarity, climate change allowances and peak river flow estimates in England. So climate change impacts may include bigger floods occurring more often, although changes in the magnitude and frequency of floods could also be due to other causes such as urbanisation or other land use change. I'm going to start by asking the question, is there evidence that floods are getting bigger? To answer this, we can analyse data from gauging stations to find out whether there are significant trends in flood magnitude and frequency already happening, and this is called non-stationary analysis. In 2021, interim guidance for non-stationary fluvial flood estimation was introduced. And using data up to 2017, this project showed that 13% of sites analysed across England and Wales showed a statistically significant upward trend in peak flows. And we recently updated the analysis to the water year 2022 to 23 to include 6 more years of data. The results show that 20% of sites now show a statistically significant upwards trend, with positive trends seen across most of England and Wales. Negative trends are less common, but there is some clustering, particularly in central and eastern England. It's important that these trends are accounted for in flood modelling studies. However, in practice, standard methods, which assume stationarity of flood estimates, are still chosen on most projects. And this is for 2 key reasons. Non-stationary methods are limited to single site analysis at good quality gauging stations with long data records. And also non-stationary methods have a much greater uncertainty than standard methods. This is a challenge, and as a result, there is a risk that we're underestimating present-day flood frequencies at non-stationary sites. This is an ongoing area of academic research, such as the Oxford University Drift Project, and we're also looking at opportunities internally for further research into this too. Climate change is included in operational flood estimates as a percentage uplift applied to either the rainfall inputs for surface water modelling or to flow hydrographs for fluvial modelling to account for the potential impacts of climate change. Guidance for applying peak flow and rainfall allowances for England can be found on the web pages that are shown on the screen. While this guidance varies slightly between flood risk assessments and capital schemes, in general, for peak flow allowances, the allowance is applied to the whole design event flood hydrograph, which is scaled up by the relevant percentage. So in this example, the 100-year hydrograph shown in blue is scaled up to the orange line by applying the peak flow allowance to the full hydrograph. And rainfall allowances are applied to the total rainfall depth for the event. So in this example, the 100-year hyetograph is shown in blue and is scaled up by applying the rainfall allowance to the rainfall depth. The link to the website detailing the peak river flow allowances to apply in England is shown at the bottom of this slide. And these allowances are based on the latest climate projections, so UK CP18, and are the result of a UK-wide study undertaken by UKCEH and commissioned by the Environment Agency and SEPA into the effect of climate change on fluvial flood peaks. Both the rainfall and peak river flow sets of allowances use the RCP 8.5 pathway results, which is the most precautionary climate change scenario. The 50th percentile results are recommended for use in most studies, which is termed the central allowance, with the 95th percentile results only used in particularly risk-sensitive applications. The allowances vary by management catchment, which is shown on the slide, and there are some significant regional variations in the allowances. And these are caused by differences in local climate projections and catchment response characteristics. Generally, larger allowances are used for the west of England compared to the east, and this data is considered to be robust to provide climate change allowances at the local level. Peak rainfall intensity allowances were modelled through a research project called Future Drainage, undertaken by a consortium led by Newcastle University, and it was funded by the NERC UK Climate Resilience Programme. And these peak rainfall intensity allowances should only be used for site-scale applications, such as drainage design and for surface water flood mapping in small catchments less than 5 kilometres squared. For modelling larger areas, direct rainfall modelling is unlikely to be appropriate, and fluvial flood risk should be assessed using the peak river flow allowances. In 2023, the Environment Agency commissioned a study to explore the impacts of using rainfall allowances for fluvial flow estimates in small catchments. This found that in some management catchments, using the rainfall allowances will lead to a higher peak flow estimate than using the peak flow allowances. However, this does not account for the impacts of climate change on antecedent conditions, which could offset some of the rainfall impacts. So as a consequence of this research, there's been no change to our national guidance. In December 2024, the Met Office Hadley Centre released updated UK climate change projections. They increased the size of the ensemble of projections, making them representative of a wider range of climate change. UK CP18, which was used to determine the Environment Agency allowances, is based on the Met Office's HADGEM model. The updated projections released in December include projections from other models in the 5th IPCC assessment report. And these additional simulations warm less quickly than the HADGEM model, resulting in more moderate changes in precipitation. These amendments to the data alter the ensemble mean, median and lower end of the distribution of future temperature and rainfall projections. They do not alter the upper end of the distribution, which represents a greater risk to flood hydrology. So again, as a result, there's been no change to our national guidance for flood estimation. The climate change allowance approach is established, it's easy to use, and it has allowed us to take action on climate change. However, there are limitations, and we recognise that it's time to revisit the approach and check that it's still valid. And this is what we're starting to look into within the Flood Hydrology Improvements Programme at the Environment Agency. I should just say that I've not been involved in this aspect of the work, but I'm presenting the work of colleagues, in particular Claire Waller and Chris Skinner. It's important to note that we do not have all of the answers, but we want to be open with our thinking so that we can work together on these issues to bring improvements to our methods in operational use. We would really appreciate hearing any feedback you may have on these ideas to understand whether we're going in the right direction. Using the current approach, peak flow allowances are applied to the full flood hydrograph as is illustrated in this slide. This may result in an overestimation of both base flow and the total flood volume, as the uplifts were assessed based on changes to the flood peaks. The hydrograph is also assumed to retain the same shape in the future, but is this realistic? We don't currently understand how rainfall profiles, storm sequencing and antecedent wetness conditions may change the hydrograph shape in the future. The allowances approach does not consider seasonal differences. Rainfall intensity is predicted to increase across all seasons. It's currently not clear whether a similar uplift in peak flows should be anticipated across all seasons equally, or if there will be differences between the seasons. Climate change allowances are more suited to event-based modelling. In some circumstances, there can be benefits to applying an alternative continuous simulation modelling approach. However, it's difficult to apply the allowances to this type of model, since it assumes that changes in extremes are the same as changes in monthly means, which might not be the case. The climate change allowances approach assumes present-day flood estimates are stationary, and it's difficult to combine the allowances where present-day flood estimates are non-stationary. And finally, there's a lack of information about uncertainty of climate change allowances. There may be alternative methods available in the academic literature, but these have not been widely adopted into operational practice. Future developments for operational use are a question of proportionality. There is a place for both simple and complex methods, proportionate to the scale and risk of projects. The current simple allowance approach, based on readily available data that's quick and easy to implement, does work well for low-risk, small-scale projects using event-based modelling, and as a result, it's likely that these methods will remain and continue to be developed. Such method development for the allowances approach could include better integration of climate change allowances with non-stationary statistical flood frequency analysis, changes to rainfall profiles, antecedent wetness and base flow to improve the representation of the hydrograph under climate change, and also improved testing and applicability to small catchments at the sub-daily timescales, which also follows on from the work presented by Felipe. However, new climate change methods are needed for more complex models to allow the full impacts of climate change, such as storm sequencing, antecedent conditions and volumes, to be explored, and this could include alternatives to uplift, the incorporation of non-stationarity within the method itself, understanding how larger spatial and temporal scale climate model outputs can be downscaled to catchment and sub-daily scales, testing how climate change impacts on rainfall profiles, sequencing, depth and frequency might be incorporated into stochastic rainfall generators, and finally exploring how rainfall runoff model parameters may need to vary with rainfall extremity. And there is already progress being made within some of these areas, and we'll be looking to liaise with others already involved in this research to better understand what is being undertaken and options to integrate within future operational flood hydrology methods. My final slide is just to say thank you for watching, and email addresses are provided on this slide if you'd like to get in touch. Thank you.
It's brilliant. Thank you very much, Donna. Really interesting. Okay, I'm now going to introduce our third speaker, Matt, who will start sharing his screen. So by way of introduction, Matt is a principal coastal scientist at Southwest Flood and Coastal, working on behalf of Bournemouth, Christchurch and Poole Council and East Devon District Council. Matt completed an undergraduate degree in 2002 at University College London, and he has a PhD in civil engineering from the University of Southampton. He has been involved in research relating to coastal flooding and erosion, including analysis of waves, sea levels and coastal landfills, and presently mostly works on beach replenishment for the Poole Bay Beach Management Scheme, particularly on licensing and consenting, coastal process analysis, and along with other local authority flood and coastal erosion risk management duties. So over to you, Matt.
Hello. Thank you very much for the introduction, Hannah, and thank you, Felipe and Donna, for your talks as well. Let's quickly stop sharing my video in case I have any connection problems, but you've seen me now, so I'll come back on for questions and answers. Okay, I hope you can see that okay. This is about a couple of regional studies of waves and sea levels on the south coast. It's waves as well as sea level, which is a bit of a bonus because it looked like it was just sea level from the topic, but hopefully that's interesting because they do tie in together well for this. I want to acknowledge my co-authors and colleagues there, particularly Thomas and Elizabeth, who work for the Channel Coastal Observatory and recently did the trend analysis on waves, which I'll talk about, which is a recent update to these studies. So just for those that aren't familiar with the region I work in, so Bournemouth, Christchurch Poole are a local authority, a joined up one, and this is within the Southern Coastal Group area and Scopac area, a group of local authorities that tend to develop research projects on fairly small budgets based on particularly important issues at the time. And we're close to the home of the National Coastal Monitoring Programme based at the Oceanography Centre in Southampton, who do a lot of surveying and set up the wave network that we'll talk about. So following the 2013 and 14 storms, which some of you may remember, they were relentless for the coast and inland as well, we were commissioned to do a study which was completed in 2020, and there's a report available online, and that covers waves and sea level trends and extremes and information about the clustering of those storms and helps to understand them in context with the observed data sets, which is the theme of this talk really. And there's going to be another report based on waves only uploaded very soon to that website. So obviously our coastline is protected by beaches, various defences, and these protect from extreme events, and we have to, for the purposes of design, try and understand the future, perhaps to 100 years in advance in cases. And what we've got here is sort of a low-hanging fruit, an opportunity to use observed data of high quality to just understand what's happening at the moment and maybe try and use that to understand the future. So this is really looking at time series data sets. At the top there, I've just shown a quick extract of a sort of tidal times observed water level time series, 15-minutely measurements, and then waves as well, half-hourly measurements from the nearshore network. So we've got gauges in the UK National Tide Gauge network, and you can get that data from the British Oceanographic Data Centre in most cases. And we also have publicly available on the National Network of Coastal Monitoring Programmes, or the Channel Coastal Observatory, as it used to be called, these wave buoys as well. And just to remind ourselves, the main interest for this, the topic in this talk will really be around mean sea level. That's what most people tend to think about, what we use in projections, but we have considered in the study the dynamics of the tides and surges that make our total still water level. And obviously waves are crucial to understand because in most cases these will actually be what overtop defences and also move sediment around on our coast. But the thing is, sea level records tend to be longer, in some cases around 100 years, and wave measurements that are consistent and suitable for trend analysis tend to be much shorter. So this isn't my work, but it's to summarise the state of play really, that the understanding around longer term observed sea level is quite well established. So compared across the record, you've got about 2 millimetres per year. Currently, it's thought to be about 4 millimetres a year, and I would recommend there's a number of kind of very up-to-date experts in this that work at the oceanography centres at Southampton and Liverpool that would be tracking this in far more detail. But what we use in flood and coastal erosion risk management is the guidance that it was referred to earlier. The government provide guidance from the UK CP, and we tend to work to around a metre for the next 100 years, and that's based on kind of mid-level emission scenarios and 95th percentile. But the range is quite large, 30 centimetres to a metre in what's expected. And we've got an example there of the Newlyn record, which is one of the better records, their annual averages, and you can see the rising trend. Waves, again, a general overview, we're dealing with, especially on the south coast, waves that come from the Atlantic, but also we get locally generated waves. And considering this spatial and temporal scales we're thinking of, it's much more uncertain and complex problem in terms of the natural variability and what is written into the kind of information and guidance we'd use for coastal flood work. And it is acknowledged in the gov.uk guidance, but there are parameters that are very important that we'll mention that perhaps are less understood. So sea level and waves in our results, this is a quick fly through really of our results. So starting at the top there, we've got the annual averaged data for Dover at the eastern end of the channel, and moving downwards, we finish up in the 9th gauge there at St Mary's in Cornwall. And we can see generally there's about a 2 millimetre a year trend across those data sets, increasing consistent with the satellite data to about 3 millimetres a year since the 90s. As I mentioned earlier, it's thought to be accelerating. And in terms of tide and surge, the changes in those, which there's a lot more figures in the report that I mentioned earlier, they're not currently thought to be statistically significant. So most of the change we're seeing is driven by mean sea level, which is largely the temperature change in the oceans and increasingly ice melt. Waves. So we looked at these data sets, and I'll show you which ones in a minute. Wave height is the trough to the crest. Wave period is a well-known parameter, and longer waves, waves that have longer periods tend to be more energetic and run up more, and that's where you might sort of look at a point of a wave and a crest, for example, and count the time the next one takes to arrive at the same point. Wave direction is quite simple, but it's very important, because that will affect how sediment's moved around and how square-on waves might hit a defence, for example. So there's a lot of interest now in the last 15 years, or growing interest in the coastal community on the south coast, especially in bimodal waves. These are where you have a swell and a wind wave component. It's a simple way of putting it, but it takes a spectral analysis of the data, and these are thought to cause more run-up and erosion. And they're not really forecast or spotted as extremes. They're a bit sneaky. For example, here in December 2015, the most bimodal month in the last 20 years at Hayling Island, or nearby Portsmouth here, where there was seawall failure, where the beach level dropped very rapidly over that month. And it's mainly attributed to this type of sea conditions we had that month. So we're looking for that. So the ones we looked at in the trend analysis that CCO did, we've got 5 buoys with over 20 years of data across this south coast area, and they've been measuring at about 10 metres water depth. And I won't go into the detail of the analysis method here, but there is much more in the report. But we looked at a number of 3 percentiles across a large range of parameters, some of which are produced by the Wavebuoy software, and a number of which we processed and quality checked ourselves. And this is, as I say, just one excerpt from the kind of graphs that show for those 9 sites the kind of trends, the positive trends, but we were looking for statistical significance. And this is summarized really here, where we've got sort of for each site this multi parameter analysis. And for example, we had 293 tests, I suppose, across those 9 sites for the different percentiles and the range of parameters, of which 60 cases we had statistical significance, and we only had 1 upward trend in wave height, which was at Hayling Island, that was statistically significant. There are other upward trends, but they're not yet, or not statistically significant, and that's about a centimetre per year. But there are a lot of changes to wave periods, especially at eastward facing sites and either side of the Isle of Wight. There were a couple of changes in average wave direction as well, which is interesting, and I'll talk about that a tiny bit more in a minute. So there was directional shift, and we corrected for the magnetic drift as well to try and verify that. And we've counted events as well. So like I mentioned, 2013-14 was a cluster of storms, but there's a way of counting it if you set thresholds and use the return periods and define a storm event across the data set. And for example, here, 2013-14, we see at Hayling Island, there was a cluster of storms. We did this also, we counted hours of swell above thresholds and bimodality as well. And it really showed that the last decade has been a lot more extreme or troublesome at the coast because of the amount of wave energy and sort of exerted on the coast. So, and we can show this now from the data, it's not just anecdotal. Just a few pictures really to close off the thinking on this. At the eastern end of Christchurch Bay, which is one of the areas colleagues work on, we've seen a real sort of problem with beach huts falling in the sea and that sediment starvation. And this isn't just here, it's happening across the region really. And you can't really yet pin this down to the sources, the waves or the sea level as such. There's sediment problems as well from legacy management, but we're seeing a real change, and it could be that some of these things we're seeing in the data now might play a part in this. Bournemouth Beach, one of the biggest beach replenishment schemes in the country. This orange line here shows the volume over time. We've been replenishing it since 1970, so boom and bust type replenishments. And incidentally, it's kind of tracked the small amount of observed sea level rise that we've seen. And we're generally noticing we have to be sort of manage the beach very well with the groins and the replenishments to keep it there and stop the cliffs being reactivated. And we're kind of at a point now where the groins are at the head of the sea wall. So there'll come a point where we've got to think about raising 9 kilometres of promenade sea wall, or there'll be other things we'll have to think about. Just I'll say a couple of pictures, because 2013-14 was extraordinary. We've got a picture there of some rocks called Pom-Pom Rock in Portland, Dorset. And in this event, it was a very powerful storm in the Atlantic, and hundreds of tons of rocks were totally demolished and broken to pieces. And another rock arch in Cornwall reduced to rubble. And each storm across this season, January and February especially, had its own characteristics. And it was really interesting how I think there was a shock to the system. So anyway, we've got this South Coast study now of observed, waved and sea levels. It's been quite engaging really for the public and engineers and councillors that don't usually study this data. And there's trends and ongoing monitoring to understand these, and updates to this is really recommended, especially maintenance of the wave buoy and tide gauge network and other data sets, especially as we start to see these signs of climate change, what it could be doing. Anyway, thank you for listening.
Thank you very much, Matt. Very interesting. Okay, we're going to move to questions now. If I can ask the panel to put their cameras on for the questions. The questions are going to be chaired by Peter Rook, who is our early careers president. Now, we've got about 10 minutes for questions, and we might not get through all of them, but what we can do for those we don't get through is share them with the speakers. And then I think, Barbara, if people can get in touch with you if they want a copy of any questions that weren't answered, if that's okay. Okay, over to you, Peter.
Right, thanks everyone. Some really interesting talks there. I think the first question is for Felipe. So it says, Felipe showed the care and thought going into modelling and projections. Is there evidence that projections are getting better or more reliable?
Thank you, Peter. I think I have very good backup of both of my supervisors in the chat, so it's very good to hear, to see that. In terms of evidence-wise, like the models, they update and they add new physical processes to it, new couple models. We're now at, I think UKCP 18 uses HGM3. With several models trying to replicate their states, and this is the point. So you're trying to replicate more accurately physical processes. The evidence is, I guess, I have to read that paper, but I'm guessing yes, that's the answer.
Brill. Thanks, Philippe. And I'm not sure who this one is directed to, but it is Could using a single climate change uplift factor for both winter and summer fail to account for how climate change has different impacts in different seasons? So I'm not sure who wants to take that one. Perhaps you, Felipe or Donna.
Yeah, I can come in here. Yeah, I think potentially there is. This is something that I flagged up with one of the as a limitations of the allowances approach. We don't currently consider or understand the seasonal differences. So yeah, I agree. There's definitely potential we could be underestimating there.
Donna, as
Thanks,
a
Donna.
follow-on question, what do you think, just based on your experience, what do you think the key differences might be? Just an opinion.
It could be down to the greater convection, particularly in the autumn and the summer. With climate change, it could cause greater rainfall intensities in the summer and autumn in particular, which could lead to an underestimation of the climate change allowances in those seasons. Yeah, it's just how it affects the climate models and on a seasonal basis.
Thank you.
Brilliant. And the next one is from Hayley Fowler. So it can be seen from recent flood events in Europe that climate change allowances are inadequate. What plans are there to update existing models for flood risk estimation, including the assessment of increasing risks with climate change? Who wants to take that one? I'm not quite sure who that's directed towards.
I think firstly we need to understand the extent to which flood events that we've seen in Europe could physically also occur within England, in this country. So in order to understand how those events could actually occur within England, first of all. But yeah, I mean, again, considering the climate change allowances is something that we're looking at within the flood hydrology improvements programme. So yeah, definitely the understanding of events that have occurred in Europe is something that we'd want to bring into any future work.
Yeah, definitely, particularly with all the flooding that happened in Valencia later last year. Okay, so the next question is for Matt. So it says, is there a point at which we can't continue nourishing beaches and need to reassess? Beach nourishment isn't a sustainable process as it has to be repeated and the sand comes from dredging.
Good question. I think we can keep beach nourishment going for quite a long time, actually, and it means that you get a lot of other benefits. It's not just coast protection, it's obviously people enjoy beaches. It is, I think, cost-wise, it's not, it's getting harder because dredge materials come from the commercial market where there's a lot of use for construction and so on, but bringing in rock, for example, or letting places fall into the sea is also, very challenging. And I think with the response to sea level, there needs to be more uncertainty before just saying blanket that it's unsustainable. But yeah, it's a challenging one.
Yeah. Thanks, Matt. And I think probably a question that a lot of people are thinking, but probably falls more onto the policy side. It says, question for Donna. With the recent update to the EA's flood mapping, are the requirements for pluvial and fluvial modelling going to change or be updated, particularly with respect to modelling that will be used to inform FRAs and planning applications? So perhaps a little bit more on the policy side. I'm not sure if you can answer that or not.
Yeah, the update to the flood mapping is broad scale NAFRA flood mapping. So there's no implications for our local scale pluvial and fluvial flood modelling. There's been no changes to our national guidance there.
And of course, we had the first batch of that data released a couple of weeks ago, with more due to follow in March. Brilliant. Thank you for that. We have a question, I'm not sure, possibly Matt. It says, in the case of gravitational flow through tidal sluice gates, low tide plays a more critical role than high tide in allowing discharge. Has the impact of climate change on low tides or low tide surges been adequately considered?
I'm just trying to read the question. It's a little bit outside the remit of what I was thinking I'd be answering. That's quite, I'm just trying to think about that because I mostly deal with open coast and beaches. Change on low or low tides, or I mean, it's still largely about. I think a big bit of this. There's been a lot recently about, or kind of in our team, it has been talked about. How much is the low tide level going to be pushed up by mean sea level? So yeah, discharge from any kind of inland area is going to be a challenge with mean sea level rise in that sense. But yeah, in terms of low tide surges, I don't know, and probably not adequately considered. It's the only answer I can come up with now. But that's quite a specialism. That the time between inland floodwater management and coastal, which is good point, but I haven't got a great answer for that at the minute.
Thanks for that, Matt. Okay, so question for both Philippe and Donna. It says, Philippe and Donna talked about not using the fluvial allowances for catchments less than 100 kilometres squared and not using rainfall allowances for catchments greater than 5 kilometres squared. What should we do in the middle gap? Maybe Philippe, do you want to have a go at that one?
Yeah, I think that's a very good question. For instance, for SIPA, the rainfall allowances are used for any catchment that are below 50 kilometers squares. And the fluvial allowances are used for any catchment that is above 30 kilometers squares. And there is this sort of gap in research where you actually need to translate the research into something that's usable for these catchments, which are very, very crucial because most of the flood risk assessments are being done in these sort of catchments that are perhaps a bit larger than 5 kilometers squares, but definitely smaller than 100 kilometers squares. So yes, what should we do? It's a very good question, and I think that's a question we need to answer in the future.
And I think, as my perspective, perhaps more as a practitioner rather than someone doing the research, I think this is an area where maybe some element of professional judgment needs to take precedent. I don't know if you agree with that or not.
Yes.
Great, thanks for that. So we've got another question from Hayley Fowler. Some of our recent work, unpublished as yet, has shown that climate model projections of changes to winter mean precipitation with warming are significantly underestimated compared to observed changes, especially for convection parameterized climate models. Do we need to account for these in model biases in our estimates of changing risk, as otherwise we may significantly underestimate changing risks of flooding, particularly in autumn and winter? I don't know if that's maybe directed more towards you again, Philippe.
I will probably say it's not, otherwise you would have asked me live.
Donna?
Yeah, again, this is, I mean, it's a good question. It's again something that we need to understand better. And again, this is something that the Flood Hydrology Improvements Programme will hopefully be able to consider in order to approve the approach we use to make adjustments for climate change.
Peter, I
Thanks
think
for
we'll have
that.
to leave the questions there, I'm afraid, due to the time. So I'm just going to reshare my screen. We're just going to wrap up the session today. So hopefully everybody can see that. Okay, so thank you very much for attending our second webinar of the series. And before you sign off the webinar for today, I encourage you to use the QR code to sign up for webinar number 3, which will be this time next Wednesday, where we'll be talking about water resources and groundwater and the research on low flows and groundwater, considering drought and groundwater impacts. So speakers include Rob Lawson, who's the chair of CIWEM's Water Resources Panel, Miranda Foster from JBA, and we're just confirming the names of the Environment Agency speakers, so do sign up for that. Some further CIWEM events to be aware of. So obviously the rest of this series, also into March, the CIWEM presidential team are doing a joint webinar with the Association for the Directors of Environment Planning and Transportation, local government membership organisation, on placemaking. I encourage you to sign up for that. 7th of March, the day later, Peter and I will be in London for the Rivers and Coastal Group technical conference for their 75th anniversary. Into April, we're doing a presidential conference in Coventry. That will be live within the next week to sign up. So hopefully meet as many of you there as possible. And I've also been asked to give you an update on Flood and Coast. So to let you know that the call for technical papers and workshops is now live. And again, hopefully I'll get to meet as many of you as possible at that event. Over to you, Duncan.
Thanks, Hannah. Yeah, so BHS has some upcoming events as well. You can see we don't have dates for them all on this list here, but do look out for them on our website. We do have one date known, which is 1st of December. We've got a conference in London about UK contributions to international hydrology. Just to mention also that BHS has a real focus on trying to have more regional and local meetings. So we're planning one, for instance, in the Pennines region, which covers all the north of England, sometime in the next few months. So look out for that as well.
Okay. Okay, so thank you very much, everybody, for attending, and we hope to see you at next week's webinar. Enjoy the rest of your Wednesday. Bye-bye.